workshop, journal, and conference paper. His main area of research is cognitive radio networks, resource allocation, and scheduling problems for wireless networks, software-defined network, that is SDN, cognitive radio solutions for 5G and 5G networks for massive IoT. So today he is going to enlighten us about cooperative spectrum prediction driven sen- driven sensing for energy constrained cognitive radio 5G networks. And I think that now I'll hand it over to you, sir, and we can start the talk.
Yeah, thank you, Dipjiti, for your lucid introduction and introducing me to all the audience over there in the session. I'm very much delighted to have this session with all of you. Actually, this particular talk that I'm just planning and I'm just preparing to be presenting in front of you is relating to the particular problem based on your prediction-driven sensing, which is prevalent nowadays based on the requirement to do a lot of things in terms of prediction-driven way and to enhance some of the issues relating to your your energy constraint situations in cognitive radio networks, cognitive radio 5G networks. So I have planned this discussion all at about say 1 hour maximum. If I take more time, then I might be skipping some of the slides. So please bear with me about that. So the outline will be like this. So basically, the problem that you have nicely mentioned that I'm just trying to discuss with you all that how the cooperative spectrum prediction driven performed for what is called sub 6 gigahertz frequency band of 5G network from so quite a long time. So solution to that in 5G network, it is trying to adopt the concept of software-defined radio. The one solution for software-defined radio is the cognitive radio technology. So we would try to discuss about that, how the cognitive radio technology can help us, along with the usage of something called your prediction-driven sensing, which is part of your cognitive radio, to be used in user equipments of 5G terminals, which will be eventually helping us to enhance the energy constraint situation. So the outline will be that I'll be trying to quickly give a glimpse about what is this full spectrum era, the era kind of your communication using going to be used for 5G like technology or 5G like network, or maybe beyond 5G network, or maybe 6G network, kind of that. The entire 5G and beyond 5G is targeting to use the full spectrum era uses in terms of the communication in our radio access arena, not in the directly core network, but in the radio access part. Then we all know about 5G new radio band. I'll try to just give you the clue about how the new radio band and where the need for such kind of a cognitive radio introduction. Then we must need the use of the cognitive radio technology. Basically, it's a software-defined technology, which will help us to overcome the problem of spectrum scarcity at lower band. 5G has 3 bands, so at the lower bands, which is basically below 6 gigahertz band. Then I'll try to emphasize the discussions in concern about the prediction-driven modeling and sensing to be done by user equipments, which is going to be termed as secondary users in the nutshell. Then finally, how the proposed solution would be, and some references based on this. So this is a work that we have done recently and has been published in an IEEE journal. So the full spectrum era is can be thought of something like this. So we can have the frequency ranges below 6 gigahertz range, as shown in the figure, the courtesy to this particular paper. Then this below 6 gigahertz range will be basically considered as low band. This centimeter wave band, meaning 6 to 30 gigahertz, this range of spectrum is going to be the mid band, and above 30 gigahertz to 100 gigahertz band is considered to be as a high band. So basically, the 5G is basically more into aiming to use this high band for the purpose of huge data rate and speed in the communication. So basically that. But in altogether, the 5G will be trying to also make operational in a way that all the existing technologies should also be prevalently working. So the low band is the place where in present time as well, 5G is targeting to use the infrastructure of 4G network, meaning the LTE network, 4G LTE network. So based on this, if we look at about this below 6 gigahertz range, the present approach to deploy such kind of a network is 5G network is not 100% standalone 5G core network. It will be based on non-standalone mode. Non-standalone mode means is that it will not have the full-fledged 5G infrastructure, but it will be using the 4G LTE infrastructure at the below for the purpose of the radio access mechanisms, or the usage of radio access mechanisms in different interfaces. So in this case actually, 5G is trying to use the new radio concept, 5G new radio. So you will find two different bands, range actually, frequency range 1 and frequency range 2, which is below 6 gigahertz range basically, mostly. And depending upon that, we'll find a crowded space of frequency range over here, where it is a very crowded space because all the devices are trying to use all this particular frequency range at this moment. And the situation is arising like that for newer and newer equipments coming in with bandwidth hungry requirement way might not be finding the sufficient spectrum band. So that is the biggest problem, which is actually addressed by ICC in terms of finding out the situation that whether the frequency allocations could be done in a fixed allocation way or dynamic allocation way. So that would be another direction actually. So altogether, if I try to figure out over here in this slide, I'm trying to say about that there are three different frequency ranges. The low range of the frequency related to the 5G communication in terms of 5G NR technology, 5G NR frequency radio band to be used, the problem of spectrum scarcity is happening. And since we are yet to reach up to this standalone mode of 5G network to be evolving, at present we are talking in terms of non-standalone mode of 5G deployment. So 4G based using the 4G based LTE infrastructure. Another infrastructure could be there in terms of sharing the frequency band based on the infrastructure called 4G LTE and 5G NR new radio. Both could be coming in, meaning NSA and 5G 4G LTE fully. So this slide tries to figure out the point that how three modes of deployment could be possible in terms of a 5G network. This is a 4G LTE based entire frequency band, 4G LTE based uses in terms of the deployment. This is the sharing mode. This is the standalone mode. Standalone mode is yet to come in real picture. It will take quite a few time from now onwards. If I go into more detail little bit, then I need to talk about that this radio access network will be provisioned by something like this. If I can say about this is a generic 5G architecture. There's something called Z node B, ZNB. ZNB is the tower using which the user equipments, 5G user equipments, will be getting the interface to access the 5G core network, and eventually it will enjoy the 5G connection, 5G communication. Different components are there: AFM, SFM, all this UPF, all these components are there as part of the core side of the 5G infrastructure, 5G architecture, where different access interfaces are also there in terms of requirements. So from there on, as per the 3GPP standardization or 3GPP specification, these user equipments would be trying to get access through this NG-ENB, this next generation ENB. ENB is the node B of 4G LTE infrastructure. So at present, 4G LTE infrastructure will be provisioning the interface to these user equipments. These user equipments will be eventually our 5G terminals, basically. So in this case, we need to think about one point, that how can we see that this 4G based frequency band can be utilized in more efficient way, such that the fulfillment of the requirement of different user equipments or terminals can be made all the day. Now here's the point, that all user equipments might be allocated the frequency bands in a fixed spectrum way out, or might be the possibility of dynamic spectrum allocation scheme could be also used. If I say dynamic spectrum allocation, I am referring towards the point called software defined radio. So some of the equipments will be equipped with this cognitive capability, cognitive radio capability, provided it can use the software dynamic spectrum allocation based allocation, which is nothing but opportunistic allocation of the spectrum bands, provided that these equipments can communicate in a software defined radio manner. So our work is related to here only, because we are trying to bring in the cognitive radio into this picture, and we are trying to bring in another thing related to the energy constraint thing, meaning equipments could be very energy constrained. So we should try to have the communication even if we have the energy constraint, meaning limited battery life and etc. etc. So from that point, the spectrum scarcity situation could be looked upon in the below 6 gigahertz band or sub 6 gigahertz band. As per the report of FCC, it is trying to show that some of the frequency bands are in heavy use and some of the frequency bands are in sporadic use. It could be spatially or temporarily or both at different spaces or at different point of time. The frequency bands in below 6 gigahertz range is sporadically used, basically. So some of the bands are heavily used, some of the bands are not 100% utilized. So you can say that in most of the time, the bands which are not fully used could be used maybe in an opportunistic fashion by some of the requiring nodes in such a way that we can have that environment sensing could be performed, and based on that, the particular frequency band where the usage is pretty low or sporadic, those unused portions can be utilized by some user terminals. So that is the point over here where we can say that these portions, these blank portions are nothing but kind of a spectrum holes. So how do you do? So this is the actually problem that FCC was looking into in late 90s actually. So where from the cognitive radio came into your picture. Now the same scenario is happening for 5G infrastructure and deployment and 5G infrastructure implementation for lower band or low band, or you can say sub 6 gigahertz band. So overall understanding about conventional radio in any wireless terminal and cognitive radio enabled terminal can be looked upon like this. This figure is nicely portrayed by Nokia Research Center. It is a kind of the scenario that All these lanes are nothing but licensed frequency bands you can consider. These licensed frequency bands will be used by the licensed users, or say the primary users of that particular license, which who has actually procured that license, got the license registration, and they can use. But this is the land probably we can consider it's a ISM band, industry, science, and medical equipment band, where the license may not be so required. Everybody can come in and communicate. But you can notice that this particular frequency band is heavily crowded because everybody is trying to use the band. So this is happening in our traditional case, in our fixed spectrum allocation scenario. So we need to overcome, we are interested to overcome from this scenario. So what might be the solution? The solution might be cognitive radio scenario, meaning wherever we find the free bands like this one, and this one, say blue colored and green colored or red colored, this lens could be used in an opportunistic way, provided the country's spectrum regulations are allowed to use so, and the technology is available for us to opportunistically use this unused frequency lens, making it more efficient in terms of using those frequency bands in terms of the spectrum utility. So this is the figure where I can see that if some of the users would be using these bands opportunistically, then the crowded scenario is resolved over here. We can say the spectrum scarcity problem could be somewhat resolved. So this is the overall scenario where the cognitive radio will come in. So this is the technology, dynamic spectrum access technology based on software-defined radio, meaning a particular user could be using these unused holes, these white regions are unused holes, and it can jump from one band to another band, this band to another band, kind of that the users will be actually cognitive enabled user equipments could be using these bands. And this very concept was first introduced by Joseph Mitula in late 90s in Germany, basically. So the idea is to see is that how some technology can be developed which can opportunistically use these unused portions in the frequency bands in such a way that the communication can be taking place by resolving the problem of spectrum scarcity. So the solution to this one in terms of technology is that the cognitive radio came up because of this effort. So altogether, I'm just putting in some of the points related to the cognitive radio. Cognitive radio functionality would be based on how the user equipment will be capable of sensing the environment relating to the changes that might be possible nearby the networking environment or radio environment. The radio environment changes could be what is called sensible by the user equipments, which we can say the cognitive radio enabled nodes. So it is the basis which will be used in the RF unit, radio frequency unit, to do some of the functionalities relating to based on the changes that might occur in the radio environment, and accordingly it will adapt how to use the different frequency bands. So there are four building blocks which will be helping us to develop the entire paradigm of cognitive radio. The first building block is the spectrum sensing, then spectrum management, spectrum mobility, and spectrum sharing. So the spectrum sensing is relating to the traditional sensing, we can say. So traditional sensing, what does it do? Any wireless device tries to perform some energy detection kind of your sensing by the RF unit. Also different other techniques are also there, but mostly the energy detection techniques, due to its computational complexity is less. The energy detection techniques are used mostly in our devices, wireless nodes, basically devices. So it senses what is called the signal strength in terms of your SNR, signal to noise ratio, based on the signal's energy level. So depending upon that, it detects whether it is available or not, or whether it is possible to be used or not in any frequency channel that is available in traditional way of using the wireless communication. So here the spectrum sensing module will get sense over here, because this spectrum sensing module should be intelligent enough to know at about the environmental changes, radio environment changes, and accordingly it needs to adopt how to use the frequency bands based on something called, you say, software defined way out, software defined radio way out. So the entire work that I'm just trying to discuss in this session is based on this spectrum sensing circuits. So two types of nodes will be there. As you can see, the licensed user equipments will be primary users, and all unlicensed users will be equal to your secondary users. So the unlicensed users will be actually capable of enabling the cognitive radio functionality, and it can do the full reconfigurable transceiver communication, wireless transceiver communication, so that it can what is called opportunistically select or choose a particular frequency band or frequency spectrum, and it can perform the communication in opportunistic manner and perform the transmissions, data transmissions. So two types of users will be available in such kind of a cognitive radio based 5G network where we are talking about. So this is the slide I'm trying to put in some of the techniques adopted for spectrum sensing in conventional way or in wireless domain. So energy detection technique is widely used because of its complexity is less, and accuracies are definitely it suffers because of the noise. But the complexity point of view, it is very useful in terms of the uses. And different other techniques are the waveform based, match filtering based, and many other, the cyclostationary based, depending upon their functionalities. So in cognitive radio as well, eventually the real sensing will be performed either probably by using any of these techniques at the end of the day, but it will be done in a software defined manner. So in such kind of sensing to the environment, or you can say spectrum sensing, which should be performed by user equipments in 5G below 6 GHz spectrum band, where the spectrum scarcity is faced by many of the devices. Target is that how can we maintain the spectrum utilization up to the high, or up to the what is called efficient way out, provided most of the equipments, most of the terminals should not be draining its energy. So energy constraint, minimum energy consumption is expected from the equipments, provided the spectrum utilization should also be maintained at a higher side. So that is the problem basically we need to talk about in this particular kind of a scenario. So when we see the conventional sensing, spectrum sensing, what does it do? So if I say that the sensing could be happening in a slotted fashion, so first slot is of duration t, second slot is of similar duration. So it might happen, it would be happening in a slotted fashion because we consider that maybe the TDMA base or the kind of that technique we can adopt for this kind of scenario. So at different time slots, the sensing could take place from user equipment's point of view. So it will be spending some amount of time for sensing, and once the sensing results will be obtained, immediately after that the transmission will take place. So while the node user equipment will be performing the sensing, it will be consuming, or it will be depleting some of the energy level, or you can say the cell life, battery life. So how do we compute during the sensing time? If we calculate like this, so overall energy that would be required for sensing, if the number of nodes will be n, if the amount of energy required for per unit of per node per unit of time, and this much of sensing duration will be required to complete the sensing about the operation of sensing, then the overall energy requirement or energy consumption will be this much. So ES will be the amount of energy. But one point I need to note down over here when we talk about the spectrum sensing, every time we ask the sensing module at your physical level of user equipment, it will be draining some amount of energy. So our target in 5G's point of view is that the equipment should not be should not be draining most of the energy only but by doing only the spectrum sensing. So spectrum sensing is required, but it should be done in more efficient manner. So that is one point. So what is the problem right now? So we want to reduce or minimize this ES. So our target will be to reduce or minimize this ES, overall energy consumption. So how can we do that in conventional sensing? In conventional sensing, uh, we do not basically target about directly reducing the energy consumption, but there are some techniques which is evolved in the literature that the conventional sensing can be enhanced or conventional sensing can be assisted with the help of spectrum prediction approaches. Spectrum prediction approaches meaning is that initially the some kind of prediction will be used whether the spectrum will be available or not, and accordingly uh, the it will be performed. Meaning spectrum prediction will be performed before the actual real sensing could take place on the particular channel, a particular frequency band. So the prediction driven sensing is possible. Spectrum prediction driven sensing is possible. One solution. If we go with that way, which many works are there in the literature in this particular direction, prediction driven sensing. So we will be spending some amount of time to do the prediction calculation, meaning what is the probability that a particular spectrum band or a particular channel is going to be sensed. That computation, that calculations needs some amount of your time. Prediction time will be required. But again, what kind of model we can adopt for such kind of predictions to be performed? In conventional way, something called multi-layer perceptron, then ARIMA models, time series models. Those are used for kind of finding out that what is called the prediction time. So basically here the probability of prediction we need to find out. So depending on the probability of prediction, if we calculate it like this right now, the energy consumption, overall energy consumption could be expressed like this way. So what is the probability of performing the prediction on a particular channel for all the nodes, with each node consuming this much of energy for sensing and this much of time for sensing. So this will be the energy consumption. So the next problem we can look at about that, when to perform the sensing after prediction. Meaning prediction is done, consider that prediction is done in spectrum prediction driven spectrum sensing. Consider that prediction is done by means of some technique, prediction technique, some models. Now, after prediction, when actually to perform the sensing? So it depends on the probability actually again. So the probability of performing the sensing over a channel after the prediction. So how do we decide this probability? That is another point. So solution to this kind of your question is that when to perform the sensing after prediction, we can think about that we can perform the sensing if the prediction says, the prediction result says that the channel is, the frequency band is supposed to be free from the users. Supposed to be free meaning it is probably not used by its licensed users at that moment. So that particular channel can be predicted to be free. We got the result, so we can probably use the particular channel. So this kind of conventional schemes, prediction-driven schemes, meaning predicting whether the channel is free or busy. So depending upon that, there are schemes. One example of this work you can find out over here in this particular paper. So this kind of schemes actually adopt like this way. So it will be trying to look at its energy consumption, considering that probability to be probability of free will be used over here. So probability of channel is predicted to be free will be used as an input, and based on that the energy consumption will be performed. What advantage of such solution is that if the prediction says that the channel is not free, that means that the sensing will not take place. Only when the prediction says that the channel is likely to be free, based on the so and so probability, then only the actual sensing will be performed. So energy consumption can be addressed over here a bit nice way. So this is the figure I can think about in such kind of scenario where prediction-driven sensing could be performed. So I am considering two slots. In the first slot, if you can notice that during the prediction, if it says that the channel is going to be busy, I'm noting down in red color way. So if the predicted prediction result could be busy, then the no possibility of your sensing. So meaning we are actually not performing the actual sensing. So meaning we are conserving the energy. But if the channel is predicted to be free, then only the sensing will take place. So in doing so, with this energy calculations, we can say that the low energy consumption could be addressed. The pros of such kind of approach is that low energy consumption could take place. But one problem is there. What will happen if the prediction is likely to be not correct? It's a false prediction. If it is a false prediction, then we are going to lose some free spectrum probably, because we are not performing the sensing. We are not going to know yet about whether the channel or the frequency band is free or busy. If it would be free, we could have been using. But the false prediction might result that the channel might be busy. So in such a case, how to handle this false prediction scenario? Because of the false prediction scenario, we are actually somehow lowering the spectrum utilization, which could have been utilized. So there is a trade-off you can look at about over here. So energy consumption, if we try to minimize the energy consumption, also we are expecting that spectrum utilization could be higher, then it is probably somewhere having a problem that because of the prediction could be false at that point of time. So another scheme came up. So this problem is coming up right now. That's right. How to enhance this poor spectrum utilization that might be produced by such kind of a conventional approach of prediction-driven sensing? The solution could be, we can say that, forget about the prediction results. Irrespective of the prediction results, we can allow the sensing to be taking place. So we can say that this probability should be always 1. Probability should be always 1. Meaning, whatever might be the scenario, we will be doing the sensing, irrespective of the prediction result. And what is the solution? What is the requirement of doing the prediction then? So we are losing that major part. If we are not utilizing the prediction part, then again we are landing up in the same problem. We boil down into the same earlier beginning problem. So this is the scenario if we go on always sensing way. So even if it is busy or even if it is free, because of the prediction result says that it is busy, it is free, then also we are performing the sensing. So by doing so, what we are trying to improve, that we are improving the spectrum utilization in a very reasonable way, or we can say it's a high spectrum utilization could be possible doing so, where joint prediction and sensing could be there. We have the prediction result in our hand, also we are performing the sensing. But this high energy consumption could be taking place because irrespective of a free or busyness, the user equipment will be adopting its actual or real sensing module to be activated. So because of that, the energy consumption will definitely take place. So high energy consumption will happen. So sensing is becoming a bottleneck, or because of the sensing is going to be performed always. But how can we improve in this case? So overall scenario, if we see prediction-driven sensing, if we go by scheme one way, then we are actually having the problem of low spectrum utilization, low energy consumption. This number 2 is expected for us, low energy spectrum consumption. But the spectrum utilization is not expected. It is like we expect that the spectrum utilization should be always high. If we go by a conventional way, conventional scheme of 2, the other scheme, meaning irrespective result scenario, then higher spectrum utilization could be there, but at the cost of higher energy consumption. But in both the cases, traditionally, in literature, you'll find that most of the time people are using multi-layer perception model for the prediction purpose. And since the behavior of the sensing would be time series based scenario, so time series prediction problem could be modeled. And if we can see that time series based data could be collected, sensing data could be collected. So eventually that 1 and 2 says that we have the trade-off between energy consumption and spectrum utilization. Now, multi-layer perceptron is okay to go with some of the applications, but in this scenario, since the time series data will be having time series data, meaning the input data in terms of the sensing data, would be having the situation of sequence dependence. This multi-layer perceptron model of prediction is not a good choice. So it has the difficulties while handling the time series data in sequence dependence way, because we know about that the pattern that will be remembered. Because of that, the computation process based on the parameters could be pretty high, multi-dimensional in multi-layer perceptron model. So because of that, it will be facing the problem of sequence dependence issue. So based on these two schemes, meaning conventional scheme 1 and scheme 2, how to maintain a good trade-off between this energy consumption and spectrum utilization, provided we can go ahead with this prediction-driven sensing. That is the problem right now we need to address. So based on this problem, we are trying to propose some solution over here. So we are heading towards our solution. So the solution could be that in the proposed case, we will be performing the sensing only when prediction is unusable to take a decision. Prediction is not good enough to take a decision, whether it is free or busy about a channel. So meaning is that how do we calculate this probability, which says that depending on the probability value, we can say that prediction is usable or unusable, because the prediction is not in a position to correctly say about the decision, whether the channel is free or whether the channel is not free, not sure about whether the channel is free or not. So if we consider like this, the same problem, then we are having this scenario. The third portion came up. So we can have a busy scenario. We may not be performing sensing or maybe performing sensing either in conventional scheme 1 or 2 way, or we might be free. We might be finding the result of the prediction to be free. We might be performing the sensing or not. But we also have a situation if we consider that the prediction result is not sufficient enough to take a sure shot decision whether it is free or busy. So this portion came up. This is the actually considerations that we are having in our particular proposed problem. So probably the channel prediction result is not sure about the status of the channel is needed to be decided right now. So in terms of both the schemes, conventional scheme 1 and conventional scheme 2, it is using the multi-layer perceptron model like this. I'm just putting a figure over here. It is going to face the problem in terms of the time series data input, where the sequence dependent issues will be there, alongside this consideration of this whether prediction is correct or not, whether it is correct or not, that decision, CUT decision. With that, the prediction has also an issues. The multi-layer perceptron model may not be a good choice. This is another problem. So solution to this, we may think about use of or replace this MLP by means of your recurrent neural network. So recurrent neural network, there are different models in recurrent neural network. The good choice over here would be LSTM, long short-term memory model. That particular model could be a good one, which actually addresses the sequence dependence problem, because this recurrent neural network have so many layers in the middle. Based on the input, it would be remembering the sequences, dependencies, and it addresses the problem to discover the dependencies on kind of your historical data. So we can take help of using this RNN. So we can probably use this one. So the next problem we can think about that how to decide the prediction is sure and when it is not sure. How to decide the prediction is sure or when it is not sure. That is another problem we need to thought of about. So for the purpose, we want to adopt the concept of cooperative prediction, cooperative spectrum prediction, meaning each of the user equipments would be performing their local predictions, and based on the results from those local predictions, if some of them will be saying that the channel spaces are free, and some other will be saying that the channel is busy. Based on that prediction results triggered by different equipments, different user equipments, we can have a decision. The channel prediction could be made on a cooperative decision way. If this scenario is not there agreeable among many user equipments in terms of free or busyness decision, then we will land up into unsure scenario. So kind of a deterministic or non-deterministic scenario we can come up with a cooperative prediction way. Now, why is the requirement of cooperative prediction? Because in many time user equipments, while they adopt the local sensing, might face some issues due to what is called shadowing, uh, heading shadowing scenario, and because of that the results of the sensing may not be producing the good outcome. So because of that we might be taking the advantage of cooperating scenario, cooperating based scenario, meaning cooperation based scenario. So this is the overall framework workflow that in our proposed work. So we are using of the sensing history data. So history data is going to be time series data here. So we will be preparing this time series data from different nodes, different user equipments. And in place of MLP, we are going to use this RNN prediction model, long short-term model, for the purpose of overcoming the problem of sequence dependence and all. And then cooperation-based prediction for the purpose of dealing with issues or errors that might occur due to local predictions and all. And after all this fourth block, we will be eventually taking a decision whether the actual ED stands for energy detection sensing would be performed by the physical sensing module or not. So that would be done in our model. So provided at the end of the day we can claim that the energy consumption is addressed along with the what is called spectrum efficiency could be, utilization efficiency could be also made up to the high. So I'm just noting down those few points. So handling of sequence dependence could be done by your RNN, then overcoming the issues of local predictions due to the some error. We can use the cooperative model of prediction. Then prediction-driven sensing is now going to be enhanced so that we can improve the utilization and energy consumption to be made low. So depending upon this, so we are trying to formulate the problem. So the problem is this: so to develop a cooperative spectrum prediction-driven sensing scheme for energy-constrained CR 5G network in sub-6 GHz frequency band or low band, which will be reducing the energy consumption while maintaining the spectrum efficiency during opportunity detection in a spectrum scarcity scenario. So this is the model. So all these SUs, all these SUs are nothing but user equipments of 5G NR network, where all these user equipments will be equipped with cognitive radio module. So cognitive capable user equipments. We are giving the name called secondary users. You can consider this fusion center for the purpose of cooperative sensing, cooperative prediction-based sensing. So this fusion center is nothing but we can consider that Z node B, Z and B could be there, and these are the full-fledged what is called user equipments of 5G network, which doesn't have the capability of cognitive, does not require the capability of cognitive behavior over there. So we can think about the network in such a way. So the sensing module or overall system module could be like this, having with different slots, similar size slots. We can have something called occupied prediction, cooperative based prediction based results, meaning say the results of cooperative prediction could be saying at say occupied occupied channel or not busy, not free, busy channel, busy frequency, or could be your free or available frequency predicted by the cooperative sensing, which are going to be falling into the category of deterministic decision. Or it could be your kind of your indecisive scenario, indecisive situation, because if we consider that the prediction might be wrong, prediction might be not giving us the correct things in terms of your accuracy, then we may not be sure about whether the decision is okay or not, meaning occupied or available. Occupied or available, we do not know. So depending upon that, we say that it's determinant state. And if it is kind of your what is called what is it, available or determinant based things, we can also consider that this could be the scenario, the sensing scenario, which could be considered as power save mood sensing scenario. And otherwise we fall on into our spectrum sensing, that could be based on sensing mood, assisted by our proposed scheme of what is called prediction driven sensing, with this assistance based on the correction in terms of our what is called the prediction results. So based on that, the combination will take place. So we consider that n number of nodes could be there, m number of channels could be there, and fusion center could be our Z node B, and the overall radio access method could be based on a TDMA fashion, and fusion center could be located according to the place, and based on that the fusing decisions could be taken on. So overall proposed scheme could be looked upon like this in this figure. So we can have the sensing history data over here, which could be nothing but the time series data, and we can adopt this long short-term memory for local spectrum prediction based on this what is called sensing history, whatever it might be available in a local in terms of the local machines way out, and it would be producing, it would be giving the result to the fusion center, who will be getting the result of the prediction list, prediction values provided by all these nodes, and eventually those values would be taken into care by this fusion model, and it will perform the fusing operation, some kind of what is called k out of n kind of fusing operations it will perform based on parallel fusion model way, and eventually the decision will be cooperative prediction decision will be given, and based on that the spectrum sensing on the channel will be actually taking place, final decision, which is basically nothing but joint cooperative spectrum prediction and sensing. So this is the overall framework that we have developed for our particular work. So some of the requirements in terms of formulating and finding out the results of entire framework of this proposed scheme would be like this. So we know about that local predictions will take place, and the time series data for each channel will be there. The LSTM will be there for local predictions, and we know that LSTM will be a good choice in terms of recurrent neural network for handling these long-term dependencies. Also, it helps us to resolve the issues of gradient vanishing problem. So this is the relation, this is the situation where in case of time series input data, some uncertain gaps might be there. So how to handle these gaps based on what is called backward propagation. Those problem can be addressed by this LSTM, because it tries to go in episode by episode way of training, and during that time it will be updating its weights and biasness in terms of the changes. So that is the advantage of using the LSTM, which we are trying to adopt. The 2 points in this cooperative prediction based scenario, the fusion center will be requiring that learning errors. Learning errors might be occurring during the time of a prediction model because of the learning algorithms. How to handle these learning errors, so alpha E. Then sensing data error. Sensing data meaning the actual sensing, when the actual sensing get performed, while the sensing data was collected from the physical sensing of the physical layer of the user equipment, some error might occur, undeterministic error might occur. So the sensing data error could be also under consideration, or required to be considered, so that we can say that in cooperative way we can address these issues of this problem of these errors, learning errors and sensing data errors, adopting the parallel fusion model. So in this case, I'm just trying to show one derivation of an equation. This equation talks about how do we perform the fusion of the result in the what is called fusion center. The fusion result will be done with the help of this k out of n fusion rule, basically. So we are trying to not k, kappa out of fusion n fusion rule. So how do we decide the value of the kappa? This is the equation we can think about, where the considerations of learning errors and sensing data errors are also addressed over there during the time of your fusion scenario in the fusion center. This happens because of the environmental variations, network environment variations due to the spatio-temporal changes. Then, based on that, this cooperative model will be taking two decision states. One is your determinant state. If a channel is sensed to be occupied or sensed to be available, based on that, it would be deciding that it would be deterministic or determinant kind of a state. Otherwise, if the prediction results could be not in a conducive way to decide about say the availability or occupancy or availability of the channel, then we can mark it as indeterminate state. So depending upon that, available status and occupied status will be collected in the cooperative prediction market. So the concept about the decision result or decision to be taken at fusion center in cooperative prediction way for a given time slot L, so we can derive this way. So if decision based or say kind of a determinate based scenario could be there, then these two results should be there. If it is not available 0, then this would be the value for DML, delta DML, or it would be 1 if it would be not busy, the channel is going to be busy, or if it would be not decisive, then it would be always minus we are considering. So considering that the number of SUs are some of the SUs are saying that it is free, some of the SUs are saying that, some of the nodes are saying that it is not free or unavailable, some are saying that available. So at that point of time, indecisive scenario could be arising, and that would be done with indeterminate way. So these two states could be, this state could be noted down. And depending upon that, we are trying to calculate this probability right now. So probability of occurrence of indeterminate state. So how do we decide about that? So based on a variable, based on the variable called XML, which would be a binary variable, and the value of this delta DML, we can have a decision about the probability value in terms of the ratio. So based on the number of slots and number of what is called channels, how many channels are under consideration for how many slots are under consideration for a particular channel, and accordingly this calculation could be taking place. So based on this, the joint cooperative sensing and prediction could be carried out. So these equations we have derived based on their formulations, where you can find out that this is the probability of free when the channel is actually free. This is the probability of what is called busy, but it is sensed to be free. It's a incorrect thing actually. The channel is busy, but it is sensed to be free. So these two probabilities would be required for the fusion center for the purpose of joint decision making, joint cooperative sensing and prediction based decision making. So depending upon that, we are trying to derive the what is called data transfer in terms of the spectral efficiency. So spectral efficiency equations could be like that. During the time of the free slots will be the probability of free when it is free. If the prediction will be like that according to the cooperative decision, then this TP by this prediction TP by T, then T as sensing by T, then data error, we can derive like this way, so that we can have overall data transfer that we can calculate out. And eventually the loss of opportunity could be 1 minus this much. So because if the loss of opportunity would be this way, then one would be the maximum value, and then minus the opportunities that we have lost. So these are actually formulations we have carried out for the purpose of perform in this cooperative based scenario. So energy consumptions. So now energy consumptions will be decided based on this indeterminate state kind of your probability value. So this probability value we'll be using. So it could be like this way. So probability of indeterminate state and the amount of energy that we have consumed, that would be the overall energy we have lost. Similarly, we can consume in a ratio way based on the capacity or based on the data that we have used and number of the sensing average sensing energy that this particular parameter. Then ratio of average data rate and average energy consumption we can calculate. So these are the formulations we carried out for the purpose of our what is called overall discussion about this cooperative based sensing. So cooperative spectrum prediction based sensing, we could think about the steps of the algorithm is like that. So initially the first step will be deciding based on local spectrum predictions, then eventually it will go on into your different other aspects in terms of predicting with LSTM and all, and finally it will be eventually going on cooperative prediction based, then finally the joint cooperative prediction and sensing based things where the final decision will be taken to be done in a physical way of sensing, or meaning the actual or real sensing will be done. But in this cooperative prediction case, we will be trying to decide whether it is an indeterminate state or determinate state. So those 2 points will be decided. Some parameters for our simulations and our calculations.
So, sorry to interrupt you, sir. I would just like to remind you that we have reached the time limit. So, I just request you to.
Okay. I'm just going to take 2 minutes maybe maximum. So.
Sure. Thank you so much, sir.
Okay.
Sorry.
Okay. So these are the parameters in terms of our calculations, in terms of our what is called simulation study. So some results we could find out in comparison with some existing the techniques, the cooperative spectrum prediction model and cooperative prediction and sensing based spectrum sharing model. So in terms of the different models we can think about, we can find it about. So based on the data collected in physical place in Roassen University in Germany, we have used that data set and we try to implement this ARIMA, then MLP and LSTM. The LSTM gives us the prediction accuracy mode. So here we are trying to show that in this result that prediction accuracy versus the number of the error that might occur in the time series data that this one our fusion model is giving us better result almost. And then here is the place where we are trying to see that the average data transfer per slot. So that average data transfer per slot is at per CPSS. We are trying to we are in a position to say about that. Then here the average loss of spectrum opportunity and average loss of spectrum opportunity in terms of different errors and the number of secondary user equipment. So based on that, we are trying to consider. So here's the point where the energy consumption. This is the main problem, main thing that we actually considered in our problem. That energy consumption has been pretty low compared to the other existing techniques, considering different time errors in different time series scenario, then number of issues and all. So some results, for few more results I'm trying to put down over here. These are actually trying to show that overall that the energy consumption scenario during this model that could be executing could be pretty low compared to the existing models in the literature. So some tables I'm just putting in over here, which is showing some numeric information which are not actually confusing. Actually, it would be not making any confusion. So some of the references based on these things actually. So and these are the references. Some of the few of the references for this, and this paper was actually accepted. This paper was actually published in IEEE Access, and we are improving this work again for different purpose. One different with different one another problem in case of our IoT, massive IoT considerations. So thank you very much for listening to me for this entire 1 hour. So if any questions, I can take them. Over to you, Deepsiti.
Yeah, thank you so much. That talk was very enlightening. Thank you so much for giving us your time.
Thank you very
And
much.
do we have any questions from any other platform? Okay, okay. So yeah, I think we have a question here from Vikram Krishna asking, how important is cognitive radio for 5G and beyond, along with other technologies?
Uh, the answer to this, it's a nice question actually. Answer to this question is that 5G is going to be operated in entire spectrum of our communication, wireless communication. So whenever the existing networks could be operating at lower band, lower frequency ranges in traditional way, over there the usage of cognitive radio will be always there because the spectrum scarcity issues for those devices will be always evident. Also, followed by that, another issue will be there. The communication at mid band or the high band, the possibility of hazards are also there. So at the point of time, the situations of cognitive kind of behavior is also important because to address the issues of energy constraint scenario. Is there any other questions?
Okay, then. Uh, okay, yeah, there's another question. Is 3GPP, especially REL 18 and 10, considering this as an important technology?
Yes, it is considering because the at this moment the 5G is going to be deployed with non-standalone mode of deployment, meaning considering the 4G LTE at the beginning. So, considering this non-standalone mode of deployment, the problem of spectrum scarcity will be always arising because it will be operating at below 6 gigahertz frequency bands. So, below 6 gigahertz frequency range is already overcrowded. So, we need the requirement of this cognitive radio. So, this release 18 or 10 is actually introducing the point about the cognitive radio. Further, the situation or the requirement that not always the spectrum allocation in future wireless communication networks could be done in what is fixed spectrum allocation. It should be done in dynamic spectrum allocation. If it goes on using the dynamic spectrum allocation or channel allocation schemes, then the concept of software defined radio will come into the picture. So, in case of software defined radio, the basis is the cognitive radio problem. So that's where the 3GPP is trying to target about. Yeah, yeah. In India, there are some issues related to the regulations of spectrum bands to be used in opportunistic way. The authorities, government of India authorities are not actually uh, clean in terms of making the policy about how would the technique of cognitive radio, where the opportunistic use of the spectrum bands could be there, because spectrum bands could be licensed. So how can we allow the license bands could be hired by somebody in an opportunistic way? So that point is really till there, but it is evolving in other places like US and Germany mostly. Thanks a lot. Thanks a lot for your nice queries, actually.
Thank you, sir. Thank you so much. So, if there's no other questions, then I'd like to we from IEEE CSSBC have made a small token of appreciation for you. And since in the online medium we won't be able to give you in person, so they'll just virtually share it to you.
Yeah, yeah, yeah. Thank you.
Uh,
Thank you. Thank you very much.
I
The
hope it
screen
is
is not.
visible. Yeah, is it visible?
Yeah, yeah, yeah.
Yeah, and I'll also request I'll also request everyone to turn on their cameras for like few moments so that we can click a photo. Chair, members of the body, all the participants.
Okay. There was it one request. Can you send me this PDF of this token, this token
Yeah,
of
sure,
art?
sir. Sure, sir. Sure, sir. I'll send it to you right away.
Yeah, yeah. Thank you, thank you. Thanks a lot.
Uh, okay. Deepak, I request you to please take the screenshot once you see everything there. Yeah. Is it done, Deepak?
Yes, done.
Okay. Okay. Thank you, everyone. Thank you, sir. Thank you for your precious time, and thank you all the participants.
Thanks a lot for considering me. It's a nice, it's very pleasure for me to have this session along with you. Thank you. Good night.
Good night, sir. With this, we disperse today's event. Thank you, everyone, for joining.
Thank you. Thank you.
Hello. So there is an attendance link. Kindly fill in your attendance if you want. Kindly fill in your attendance.
Hello.
Yes.
Yeah. Is there anything left, or like I have some?
Yeah, just the attendance, like a few people.
Okay. Okay. Yeah, I'll fill it up. I'll fill it up.
So I request everyone present here, please fill in your attendance, even if you are volunteers.
Okay.